saturated. So and the density is uniform. So like this, what happens inside the nucleus is what I see what we encounter the nuclear force as well as the electrostatic force. Then I will take help of to explain the binding energy. Binding energy, yesterday I gave a formula. One more we have it's called like a liquid drop model. This is can be asked in general passage. So let me just elaborate it. It's not there in syllabus, but still they can ask you in general passage. So regarding the nucleus, what happened? They just proposed it here. So what are the binding energy? Binding energy, I'll directly write formula. Then we'll express all the quantities one by one. Plus or minus C5 e to power of 4 by 3 minus 4 by 3. Okay, like this, what happened? There's a total binding energy of nucleus. What is A? A is a mass number, I think, mass number or total number of nucleons. So the binding energy depends on the first one. What is that C1? It depends upon also the mass number here telling. So if as the number of nucleons increases, what will happen to the interaction? Will decrease. If more nucleons are there, so what happens to the interaction between the individual nucleons? Will decrease, no? So a given nucleon, what happens? Suppose the previous discussion what we made, the one will interact with only surrounding. So that particular nuclear interactions what will also contribute for the binding energy. To address that nuclear interaction, the interaction between nucleons what we have brought this one, and the value of C1 practically what happened, we are able to generate it is equal to around C1 is equal to 17 point or 15 point. Not exactly, it's average value. Different books, they give slightly different values. Mega electron volt. Now what is this? So what is the conclusion we can write? A given nucleon will interact with only adjacent neighboring nucleons, and because of that, what happens? The binding energy, shall I say, that depends upon the directly proportional to number of nucleons. So what is the reason for that? The binding energy, I think we'll write individually. This C1, we'll write exponential here rather than, because a given nucleon. Now, why do that energy? I'm giving explanation. A given nucleon will interact with adjacent nucleons only. This one, and because of this, what happened? With nearest or adjacent nearby nucleons only. So because of this, so what you can say, this effect gives a binding energy term that is proportional to number of nucleons. So if the more number of nucleons are there, as binding energy will increase here. So therefore, this effect, and as the distance increases, what happen again? It gets saturation mode, means the nuclear force will get saturated, and the interaction will decrease here. So this interaction depends on what? If more nucleons are there, more interaction. Shall I put in simplest way? See, like it's not that, see, like if there are, so what is the meaning of this? If there are two are there, so one interaction, 3 nucleons, how many interactions? 1, 2, 3. If there are 4, how many interactions? 1, 2, 3, 4. So like that, as the number of nucleons increases, what happens to number of interactions will increase. So the number of interactions also will contribute for binding energy. That's a logical way of thinking, nothing big. So what we can say that one, This effect gives a binding energy that is proportional to number of nucleons. S.C. Verma, he has discussed all property of nucleus. He didn't write equation. You see the theory, what all he has explained at 1.5 page. Nothing but this equation only, but he didn't write this equation. Not to trouble students here. Just I'm bringing explanation. What all he has wrote that explanation of, for that I'm expressing mathematically. What do you mean by that? Okay, this is about, so the binding energy also depends on what number of nucleons. Okay, next after this. So what is that next term? C2A minus C2A to power of 2 by 3. Those nucleons which are on the surface will have less interaction. Those nucleons on the surface of the nucleus are less tightly bound than those in the interior. Because any reason? Because they have no neighbor outside the surface. I think I'll write only this much. Further, we need not to elaborate much here. Again, everything, the diagram is there. Look at the brown color one. What is the problem with that? Just look at the number 41. Yes, it is able to interact with 43, 42, 40, or maybe to some extent these things. So they're not tightly bound, no, because there are no nucleons on this side. So they're not tightly bound, so they're loosely bound. And moreover, if electrostatic force will come, still more it is, no. If you look at the 43, there'll be nuclear force will be acting, but it will be very less interaction will be there. And so what happened? The electrostatic force will be dominating. So these nucleons are very loosely bound. So what they do, they decrease the binding energy. So those nucleons which are on the surface, what happens? They are not tightly bound. They'll have less interaction, and moreover, electrostatic force will also come. So to express that effect, will bring like this. That's why the negative sign. No? Why negative sign understood? So the reason why we bring negative sign, and it is proportional to radius. No, it also radius of the nucleus. So as the mass number increases, radius will also increase. So therefore, the expression is adjusted like this here. It's simple. What is the surface area? 4 pi r square. And what is the radius? I think r square. And what is r equal to? R naught a to power of 1 by 3. Why a to power of 2 by 3 will come? Able to understand. Substitute this r there. Surface area of the nucleus equal to 4 pi r square. And we know radius equal to r naught a to power of 1 by 3. So this surface effect what happen will decrease the binding energy. That's what I mean to say. That's why negative sign is brought here. Why a to power of 2 by 3? We can give some explanation like this here. And then, so next again, what is the term? C3Z, Z minus 1, A3. Denominator is there. Every one of the Z protons, that proton will repel Z into Z minus, or Z minus will repel Z minus 1 protons. Z minus other protons. This is what practically happens here. So now the total repulsive electrostatic potential energy. So you know electrostatic potential energy, what we write, this should be equal to say some q charge z with other all z minus 1 4 pi epsilon naught r, and what is this r we can bring it as r naught a to power of 1 by 3. So why the denominator a to power of 1 by 3? Because it has come like this. And why z into z minus 1? The interaction. When I add up all roughly, so we'll end up equation of like this. So every one of z proton will repel the other protons and the interaction potential energy. I think this will come in the next step. The electrostatic interaction potential energy is given by, so because of this, and what is electrostatic repulsive force? It's a repulsive force, no? Electrostatic interaction potential energy. So what happened to the protons? Constantly they'll be experiencing the repulsive force, and that repulsive force, what happened, will try to decrease the binding energy. So what you can say, the repulsive force between protons will decrease the binding energy of nucleus. Why it will decrease? See, what do you mean binding energy? If they are more tightly binded, more binding energy. So this repulsive force, what will try to increase the distance between the nucleons, no? So the binding energy will decrease here. The repulsive force between protons will decrease the binding energy of nucleus, or will increase distance between nucleons. So therefore it has to be negative. So it will contribute for negative. The binding energy depends on this interaction also between the protons. So more number of protons open, definitely open. Yes, definitely the stability will decrease here. The fourth one, no? What is the fourth one? C4 by A. Yeah. This is something based on stability. For stability, so we know A is equal to n plus z. A should be content. For stability, what the nucleus will do? Z should be as small as possible. No? If n is more, for stability, if n greater than z, that will n should be greater than z for stability. What happens if n is less than z? If more protons are there, what happens? More repulsive force will come, and it will decrease the stability. So for that purpose, a nucleus must possess, it should try to have more number of neutrons than protons. So definitely that n minus z, what happen? If it is greater than 1 s, then definitely what happen, you can say it's said to be more stable. So in a, and that what happen, it should be in the lower state, that one. So that particular thing what happen, we express using this quantity, and it's also negative. So further, what you can write, A equal to n minus z, no? So A equal to n plus z. So if you write A equal to n plus z here in this equation, this will lead to n minus z. And below what will happen, we'll get n plus z. So here this quantity should be more in the denominator, and here the n plus z, that one. So like this what happen? So that n minus z is what matters a lot. If n minus z, if value is greater, no, then it's said to be more stable. At the same time, n plus z will come in the denominator. So that particular parameter what happen will affect the binding energy of the system. So for that purpose, what happen, we have introduced that quantity also. Even the number of neutrons, protons, their number matters a lot for the stability of that atom. So that will also have influence on the binding energy. In short, I'll write it because at your level, I think very difficult to go in depth, because again, I have to go for quantum state. I'll just wind up this one. And the last one, it depends upon the pairing of nucleons. Suppose say the pairing can be positive or negative. So, pairing of protons and neutrons, that one. So if both the pairing can, what happens can be such that it can be positive or negative. If both Z and N are even, pairing of what? Pairing of proton and neutron. Nuclear force favors pairing of protons and neutrons. Okay, that's one. If the pairing is even, then it'll be positive. Pairing is odd, then what happens? It's said to be negative, that one. So like that, even the pairing of neutrons, protons also matters here. So just okay, the pairing of nucleons or pairing of protons and neutrons. Even this will also influence the binding energy, and the pairing can be positive, negative. If both Z and N are even, less binding energy. If both Z and N are odd, then what happens? It will be zero, or it can be positive here. So that pairing, again, we have to go for Pauli's exclusion principle. So based on that, it will come. So like this, the binding energy, it depends on all so many parameters, and roughly what happens, C1, C2 experimental will determine. I think in books, different books, they give a different value. I'll just leave it. Let's not bother here. So therefore, the stability of particular nucleus, if you are discussing, not just like one parameter. So all these are to be considered here. And the binding energy, in fact, depends. We don't use this method. I already shown yesterday how to calculate binding energy. I'll calculate the mass of the nucleus and the mass of the nucleons. The difference of that what will give the binding energy, and binding energy per nucleon. The overall the idea of this particular thing.